All right, so can y'all hear me? Please put in the chat if you can. Okay, can hear me? Here, Starbase, you be by the computer, and I'm gonna take the mic. Oh, all right, can y'all hear me with the mic? All right, cool. Let's go. All right, so welcome to the second session of Learning Labs. So this is going to be a bit more computer science based, a bit more coding based, or it's all computer science, but this is going to be more coding. So we're going to be taking an in-depth look at Qiskit and some of the resources that they have to offer in order to help you guys appropriately learn and practice for this exam. So before we delve right into Qiskit, we're going to look at some of the resources they have to offer. And what I mean by that is we're going to be looking at the Qiskit textbook. So right over here, if you guys want to go to your web browser and check this out, this is the Qiskit textbook. And be careful, this is the beta version that I'm looking at right here. So this is still a project that's being worked on, but it's really good because it has a lot of interactive features that the previous one didn't really make as available as this version has. So make sure you go to the beta. And the place I recommend to start looking at least is going to the introduction course. And we'll be looking at one of these, we're going to be looking at one of these pages just to show what type of things there are available and how you can practice. So we're going to be going to the introduction course page, and we are also going to be going to the describing quantum computers page. And a lot of these activities are going to be reviewed from what we presented last time. So we go to describing quantum computers. We can basically just start with this page. So we're going to be going over just a few of these sections right now, and just we're going to ask some questions, go through reasoning, what you guys think. If you guys have no clue, we're going to talk solution. So first of all, let's talk about describing quantum computers, and we're basically going to read some things. So this chapter will introduce different mathematical objects and notations that we're going to be using to describe quantum computers. Symbols, equations, and specialist vocabulary allow us to communicate and work with maths in a very concise way. They're incredibly powerful tools, but they also come at a cost. They are difficult to understand if you don't know what all the symbols mean. This can alienate people, as I'm sure it's happened a lot. To counter this, in this textbook, these equations are interactive. You can move your mouse over symbols to see what they mean, and we will also sprinkle in some esoteric words so you can start speaking the language of mathematics and quantum computing. And you can see explanation of these words by moving your mouse over. Like, for example, you don't know what esoteric means, there's a definition right here. So you can just look at the red underline. So let's go over real quickly what amplitude. So a classical probability is often represented by a real number between 0 and 1. But amplitudes also can have a direction. So see over here how the arrow is pointing downwards. So this makes an amplitude a perfect candidate to be represented by a vector. So as a complex number can also be completely described by both a magnitude and a direction, as a vector has. But in this course, we will only work with amplitudes that can point in two directions. So that's either left or right. And we won't worry about angles for now. So as you can see here, going from an amplitude which has a magnitude of 0.3, so about 30% of the area is taken up in the circle over here, and the arrow is pointing downwards. So that's what's called a phase if we treat the circle like a unit circle. If we rotate 270 degrees from 0, then we'll be ending up in this direction. But if you square an amplitude, you will end up with only one number. That's what's called a probability. So if you square 0.3, you'll get 0.09. And this makes the math a lot simpler, as we can now describe any amplitude as a number between -1 and 1. If the number is positive, the amplitude is facing forward. If it's negative, it's facing backwards. It turns out that this is still enough to do interesting things. And so now we're going to have a quick quiz question. So which of these is a valid amplitude, but not a valid probability? Does anyone want to take a guess? Yes. -1? Yes, that is correct. So let's select -1, and it's correct. So you guys want me to explain why this is correct, and go through why everything else is incorrect, or is it unclear to anyone? No? Yes. Okay. So this is a valid amplitude over here because it's a number between +1 and -1. But it's not a valid probability because probabilities can't be negative. Whereas all the other ones, so 1.01, it's not a valid amplitude nor a valid probability. And 1/3 is a valid amplitude, and well, -2 isn't about negative square root of 2 isn't a valid probability, and 1/3 is both a valid amplitude and a valid probability. So that's the first thing. Yeah, it's neither. That's what I thought. Or I might have said something. Sorry if I did.
Yeah, if you square it and it's negative, it's not gonna be a valid amplitude because if you get the probability from it, it would have been negative, which is doesn't make sense.
All right, so that's just a quick quiz question. And for state vectors, we saw in the last page that we can predict the behavior of a quantum system by keeping track of the probability amplitudes for each outcome at each point in our computation. So we also saw that for n qubits, there are 2 to the n possible outcomes. So since we have a matrix, since we have a column matrix with 4 entries, that means we are representing 2 qubits over here. So since there are 2 to the n possible outcomes, we can store these amplitudes in lists of length to the power n, and we call these vectors. Since these vectors describe the state of our qubits, we call them the state vectors. And so here's an example for a state vector with 2 qubits. So we can see that 2 of them have 2 of the entries have square root 1/2, whereas the other 2 have 0. So spend some time reading the tooltips on the equation above, and we have 2 other quick quiz questions. So real quick before we get started over here, I want to explain this. So for each of these entries, does everyone know how to count in binary? Everyone does? All right, cool. So the first probability represents the state, or the first amplitude represents the state 0, 0. The second one represents the state 0, 1. We're going from top to bottom. The third represents 1, 0, and the final one represents 1, 1. So in the state vector above, what is the amplitude of the outcome 0, 1? Yes, it is square root of 1/2. So if the state vector above describes the state of some qubits, what would be the probability, not the amplitude, the probability of measuring the 0, 0? Yes, correct, 1/2. All right, so adding and multiplying vectors, we're going to skip a few of these sections for now. We're going to skip this section for now, but we are going to continue with quantum operations since that's what we went over last time, how to manipulate qubit states. So now we know all about the different states that our qubits can be in. It's time to look at how to represent the operations that transform from one state to another state. In the same way, there is a transition probability that a certain action will transform a coin from heads to tails. There is a transition amplitude for each starting state and end state for our qubits. We can describe any quantum operations through these transition amplitudes. So before the operation, you can have a certain set of amplitudes, and after the operation, like you apply a certain set of gates, this is what happens after you're done. So what possible transformations are there? And how can you get them? Say we have a starting state A that's transformed into a new state B. We want our representation to cover every possible transformation. Then each amplitude in A must have a transition amplitude to each amplitude in B. So an n cube, so another quick quiz question, and this one's a little more complicated because we didn't really go over this last time, but still, I think it's worth thinking about this, and overall, it helps represent many gates and qubit states. So an n qubit state vector can contain up to 2 to the power n amplitudes. What's the largest number of transition amplitudes we need to represent any quantum operation on n qubits? So I would say my hint over here is to take a close look at this diagram. And if you see the network connections between that, that will help. So this is for a 2 qubit state. But how many do you think, what do you think the answer is for this question over here? Yes, to the power n squared, since there are 16 total connections between before operation and after operation. So each one of those amplitudes has a line going to each of the amplitudes in B. So yes, that is correct. And so this is a nice diagram to demonstrate what transition amplitudes are. And this also plays into multiplying matrices. So if you want to go from t sub 0, 0 to t sub 0, 0, that's what you'll have. That's what you'll multiply. And so on and so forth. T of 0, 1 goes to t of 0, 0. So the first row is all going to help add up to the first amplitude in the resultant state. And the second one will go to 0, 1. Third one will go to 1, 0. Fourth will go to 1, 1. And so we have an example over here that's the CNOT gate, which we'll be dealing with shortly. I'm not sure if we'll do it this class, but maybe next class. So, quick quiz. What is the transition amplitude of the CNOT operation as shown above, transforming the state 1, 0 to 0, 1? Looking at this diagram up here, the U matrix will help. So, what do you guys think? It is 0. All right. And finally, let's just read this real quick. So here's the matrix for the H gate. So that's 1, I'm sorry, but I'll write it over here. All right, so that's the H gate. It's square root of half and 1, 1, 1, negative 1. So yeah, so and here's the matrix for the H gate that we saw in the previous page. We use the same rule for multiplying a matrix by a scalar as we do vectors. And when we want to see what effect an operation will have on some qubits, we multiply each transition amplitude by the amplitude of each state in our input state. Then add up the amplitudes for each state to get our output state. So that's just basically telling us how to multiply. This is exactly the same as multiplying along each branch in a probability or amplitude tree and adding up the total probabilities or amplitudes tested. So yeah, that's just a quick overview of one of the sections in the Qiskit textbook, and all of these quiz questions can help you with your understanding of it. Now, does anyone have any questions at this point? At all about anything? Yeah.
Why is
No questions this week.
but in the Hadamard gate, why is the fourth bottom right -1 1?
Why is it -1? I'm sure about that actually. It's not a stupid question, by the way. It's a really good question. I actually don't know.
They did something about it being the amplitude from oh, I don't know how that makes sense.
Well, it's the gate that helps put the cubic in superposition. This is the gate that helps does that, and we'll demonstrate that shortly.
Yeah, we'll look into that when we see of how unitaries are made. So all these gates, there's something called unitary matrices, and deriving them, you'll see why that -1 or where it comes from.
Yes, so,
It did come out.
Yeah, it does. It seems everything is symmetric except that bottom right term.
yeah.
Definitely.
So, now we're gonna start actually coding with Qiskit in the terminal.
Which section is the book for this?
Oh, so if you go to the Qiskit textbook, the new one for beta, then. Yeah, so. Yeah, so you wanna go to the introduction to quantum computing section. You able to see that? Yeah, so
There's
click on
like-
introductory.
there's a drop down. This is like browser.
If you scroll down all the way, there'll be a pages section and it's all describing. So this is just an example of one section, but if you guys have the time, I encourage you to go through as many sections as you can to test your understanding. But anyway, I will stop sharing and let Sarvesh take it away.
Can we turn on this screen too?
I'm gonna stop sharing over here. You start sharing the laptop.
No, can we share this screen? Like the laptop screen? Can we turn it on?
Yeah, just on the side.
Yeah, can you do that real quick?
Yeah.
Okay, so last time, I'm pretty sure we left off. We did the equation, right? For what happens when we apply a Hadamard gate onto the 0 state. And then onto 1 state, and we demonstrated where interference, like what that even means. You guys remember that? Someone, it's okay, you guys tell me. Oh. So this, let's say.
Yes, we will show you exactly how to get here.
Oh, you feel free to, like this.
Okay, so do we want to start by helping them set up quantum experience?
Yeah.
Okay, so we're gonna take a bit of a detour and we'll show you guys this after, but real quick, we want to help you guys set up IBM quantum experience. So let's first go to IBM quantum experience. And so this is the site. So let me log out for now. So this is a site that we can use to run all these quantum experiments, whether it's the composer or if you want to write a notebook in Python. So you guys can go here and first you guys can create an IBM quantum account if you guys don't have it. So we'll just take about 2 or 3 minutes to do that if anyone has any questions along the way. Yeah.
So the reason why we're even going here is because they offer this like IDE to code on. And if any of you guys have coded in Python before, there's something called Jupyter Notebooks that people also use, right? Some people have heard of it. And this IBM's like composer is almost the exact same thing. So later we can show you guys how to set up Jupyter Notebooks, but this is the fast, easy way to just save any code that you've written on it. If you want to run it, you can do it, everything from here. So
Yeah.
that's what we'll be using for that.
Yeah, so Qiskit gets preloaded online and that makes it a lot more useful. That prevents you from having to download Qiskit onto your local machine, which you can still do and go through the setup process for that. But doing this makes it a lot easier to experiment easily. Does anyone have any? Yeah. That's kind of strange.
For you guys can also just log in through or create an account through Google.
Yeah, I'm pretty sure. Okay, so if you go back, you have this Google option right here. You can click this G. Or if you have GitHub or LinkedIn, if you prefer any of those things.
Or through IBM. I always log in through Google because it's super easy and then IBM has your email so they can send you information.
Yeah. Is anyone having any troubles so far other than the organization? Oh, we're gonna show you all of that, don't worry. So is anyone having trouble creating an account, or you guys all have accounts by now? Everyone good? All right, so then let's continue. So we can log in, go to Google. This is my personal account. So can everyone see a page like this? Right? Okay, so you can either go to the composer, which is what we demonstrated at the end of last class. So just a quick look at that. You can drag and drop gates, play around with those, and you can see the code off to the side. But we are primarily going to focus on running Python notebooks today, so Jupyter notebooks. So we will instead be going to the lab. So if you go to Launch Lab, so you can go over here and you could go to, is this the one that, am I using the wrong account? Hold on. Just give me a second, guys. Okay.
Yeah, so here, when you're on to this page, everyone see that? Okay, so we want to go to, Python 3 IPyKernel, and the one that has the weird here.
Yeah, the Qiskit sphere. It's really strange.
Oh, yeah, it should be somewhere in the middle of the screen. And,
Okay, this is kind of strange. I don't know where we prepared or went, but let me try my other account real quick. Just give me a minute.
I can handle it.
You sure?
Yeah.
Okay.
Okay,
So yeah. So if we go from here, you can see it comes preloaded with Qiskit. And
okay,
just give us.
yeah.
Here, I can just turn it back if you want.
Okay, so if everyone's on this page, okay, first thing you probably want to do is save this. So, file, save notebook, right? Oh, sorry, we want to rename it too. So rename it to something like demo, something. Okay. And you see like you're thrown a bunch of information. So importing a bunch of stuff. This is just saying, okay, I'm going to import these things from Qiskit, and a lot of these things we're not going to use. Okay, this is just for any generic user, but we will take you guys through what we are going to be using. Okay. So as I said before, last time we went a bit in depth into the matrices, right? Do you guys remember the like 0 state, 1 state?
All that sort of stuff, the
Agency.
plus state, minus state.
Yeah.
Yeah, sure thing.
So first of all, these are our two basis states, correct? It's what's called a column vector. So these are called matrices or column vectors. So literally they're just two slots. So the top one represents, you guys remember, the 0 state. The bottom one is the 1 state.
So real quick, I'm just gonna reproduce,
And
that's fine, no, it's okay.
if there's a 1 at the top right, that means you have the 0 state. Right? If there's a 1 at the bottom, that means it's the 1 state. Okay. And there are some matrices that we can use to change from one state to the other. So in classical computing, if we have a 0, we want to go to 1, right? We would use a NOT gate, right? So the quantum equivalent of that is this matrix. We call it the X state, and we will go into why that is called the X state. So this is the X state, okay? One's along the diagonal in a mirror image to what's called an identity matrix. If you guys have done any sort of linear algebra, there's something called an identity matrix, which if you multiply through any other matrix of the same size, you'll get the same thing. It's like multiplying a number by 1. You just like 1 times 5 is 5. Yes. So the identity matrix is a gate. But usually we won't, like in math, you won't really write out like 1 times 5 in like any of your equations, right? You usually simplify that. So if it's like 1/5 times 5 times some number, we'll be like, oh, 1/5 times 5, that cancels out to 1. And then we just ignore that 1. Usually like that. But yeah, technically there is an identity gate. And yeah. So this is so far all been in our heads about just how a gate affects a matrix and a state. But now we will move to how you guys can tangibly, not tangibly, but visually see that in 3 dimensions.
Yeah, so just for those of you guys who are listening online or are gonna be listening later on, basically what Sarvesh just went over is he went over the basics of the identity gate as well as the plus state and the minus state. So this is a visualization of the plus and minus state, and if we want to look at some gates, these are the 3 X, Y, and Z gates, and we also have the number gate. And what's not mentioned is the identity. Or Sarvesh mentioned it, but basically what it does is it applies nothing really. It just produces the same state over. So yeah. Now, do you want to take it away on code?
Okay, so one thing is, you know how we've been calling this a state or a column matrix or a vector? So there's also something called a state vector because it is a vector which represents our quantum state. Okay. And what we can do is we can actually view this. Oh, this is down here. Give me 1 second, guys. Okay. What we can do is we can initialize a state and view it in Qiskit, right? So first, how do we create a state? Okay. So we're first gonna initialize something called a quantum circuit. So anytime you're gonna do anything remotely quantum, you're gonna want to do this. So we'll start off by saying QC is equal to quantum circuit. And if you guys have any knowledge of coding beforehand, this is but I'm a Java programmer, so I don't know much of this, but this is like initializing an object, right? And yeah, so you're creating the quantum circuit object. And now anytime you want to add a gate, do anything with the circuit, you're gonna say QC dot.
You should specify.
Oh yeah. So along with in our parameters, we're gonna usually put our how many quantum bits we want. So how many qubits. So let's start with 1 for now. Okay. And then if you want a classical bit, you can do comma 1. or how many ever, but we don't need that for now. Okay. So we have a quantum circuit now, and yeah, if we press Shift Enter, by the way, that's what runs a code cell. It doesn't give us an output because we haven't told it to print anything or display. Okay. So now let's add a gate to our quantum circuit. So by default, we have one qubit that we said, and by default, they all initialize to the 0 state or the ground state. Okay. So if we want to actually look at the circuit right now, we can do something we can call the draw function. Okay. And now if you press Shift Enter, we have this line. Okay. This is an empty circuit. We haven't really done anything yet. So what was one of the first gates we went over? We went over the NOT gate, right? So let's add that in between those two lines. Let's say QC dot, and what do we call the NOT gate? X, exactly. The X gate. So we say QC dot X.
Yeah, and you also want to specify which wire or qubit, in this case wire, each wire represents a qubit. You want to specify which wire you want to apply this gate to.
Mhm.
So first you call the name of what your quantum circuit is, and then dot what gate you want to apply. So in this case, we want to apply it to the first gate, but everything is counted from 0. So even though we have one wire, we want to say QC dot X of 0.
Yeah. So how they internally do it is you can pass in an array.
Yeah, you just count from 0.
Yeah. So what this is doing is internally all the qubits and all the control bits are indices in an array. So all the qubits are part of an array. Yes. Oh. Okay. Yeah. So to answer your question, they're all the qubits are an array. So the specific index that we want. So if we have one qubit, it'll be in the 0th index, right? So just like that. So we would say QC dot X applied to the 0 state or 0 qubit. And now if you press Shift Enter, you can see that you applied an X gate. Okay.
Are we allowed to see the state on this, or is there like, or not?
What do you mean?
Like it's like two flat lines and then a box. Do we get like see what these like the lines represent?
For which one?
Yeah.
Oh, this?
Yeah, like like it's like a cube and a half.
Oh, this is the line is just like represents your circuit.
That
Okay.
represents a qubit.
Yeah.
And the X is representing the gate we're applying to. So we're representing which gates we are applying to which one.
So here it'll be more clear if I add some more gates. So let's just add another NOT gate. Okay.
Oh, okay, I see.
Yeah. So you can, how I like to think about it is like the qubit starts on this side, like at the Q, and then as it travels through the wire, X gate gets applied on it, X gate gets applied on it, and then it's done. Okay. So now let's go to the point. No, you have to either calculate that, or, which we're gonna see next, we can use something called a block sphere to visualize what our qubit state currently is, right? Because right now, if we want to know, we'll either have to like calculate using the matrices to know what state we're in. Okay, so everyone's drawn their circuit, correct? So what we can do is in this next cell, okay? Well, we're going to, oh, actually we have to import one extra thing, sorry. Up here, what we can do is we import, let's see. Okay, so we say from Qiskit dot, Okay, dot quantum info. We're going to import state vector. Okay, and then if we press Shift Enter, that'll load that cell. Okay. No, it's not. It's all one word. Yeah. Okay. So with this, what we can do is we can visualize our qubit right now. So in this new cell, we're just going to put plot block multi-vector.
So what you guys. So what you guys are gonna see is what's known as the block vector, or the block sphere rather. The block sphere helps us to visualize quantum states using a three-dimensional unit circle. And so the extra axis is the complex axis. So we have an x-axis, we have a y-axis, and we also have a complex axis.
Okay, so within this plot block multi-vector function, we're gonna say state vector dot from underscore instruction. Then we pass in our quantum circuit, which we named as QC. We put dot data. I know it's a kind of a long one, but hopefully y'all see it in one line on your screen. Okay.
We're gonna explain what each of the things mean.
Yeah. Okay, so now we have a three-dimensional representation. For now, you can ignore where the 0 points to. We'll get to that. So what's happening right here is we have an x-axis, y-axis, and then our vertical axis is our z-axis.
Wait, hold on 1 second. Yeah, you have a question?
Oh,
Hold on.
what is the error saying?
I think I mistyped the import state vector.
Oh, okay. Should be. Did you guys run that cell?
Can't find it, say X naught, like base dot X naught.
Yeah, you can. So the reason we do have a graphical bit is when we measure, like when we measure a state, we want that state to be stable. There would be a value like 1 or 0. We want that. We'll say that.
We can use that one. Yeah, it's like the bit is like a temporary.
Yeah, you just measure. It's literally like if you have an answer like on a calculator, right? Because think about it as a quantum computer. So if you have an answer, you want that answer to be either shown on the screen or stored. We don't want to store that in a quantum bit, right? That would be really great. Yes. Yeah. Okay. So, previously, there was. So it doesn't have to be fully 0, or it doesn't have to be fully 1. It can be some common. Okay, so yeah, because it is some we can use that to make computations where but things cancel out each other. We'll be going into that. And also, I'm glad you brought that up. The whole point is that a last round you're learning all the you can do it. So now you can visualize. Yeah. I don't I Because right now you're just saying, but once I take the this out, because you don't know what you're doing. Now you think. That was like my friend, and not like it. I'm gonna try to put all like the board. And okay, everyone thought there how to like print that the multi-vector block here. Yeah, it's a long like set of instructions. So as a coder, usually you will put this in like its own like easy to run method that you could just call like run create block sphere and use it. Oh. Any other questions? Everyone got it working? Okay, so we go down here. So we have this three-dimensional representation and it literally is a ball. Okay, so this is not a qubit, right? But it's a representation of a qubit. So as you can see, our 0 state is at the top and our 1 state is on the bottom. Okay, so what was the gate that we said that can transition between 0 and 1? X gate, right? So if you apply not gate to 0, it should flip to 1. So I have 2 up here, right? 2 X gates. So if I comment one out actually. So comment in Python, by the way, is the hashtag or the pound sign. So if we do that, that means there's just one X in our circuit. So the qubit started on a 0 state, and now it flips to the 1 state. Okay. And like we saw before, if I apply 2 X's, right? So we initialize the quantum circuit, not gate, then another not gate. What we get is a double flip, and it's back to the 0 state. Okay, which makes sense, right? Anyone have any questions so far? QUBIT. Yeah, no worries. Okay, and so now that's literally 2 states so far. We have the entire rest of the sphere, right? So what other gate did we talk about, right? Besides Hadamard, right? So this is going to be one of the crucial gates that we use. Okay, so I'm going to comment out this X so far. Okay. And we're just going to do QC.H. And then we apply it to the 0th qubit. Okay. Okay. So now our quantum circuit looks a bit different. It's just at H. And now our vector, remember, it starts up at the top of the 0 state, and now it goes to the points in that X direction, right? Well, we call this the plus state. Okay. And as you can see, it's right in between the 0 and 1 states. So you can actually think of this as, okay, it's right in the middle. So if I measure it right now, do I know where it's going to be, if it's going to measure 0, 1? No, right? It's going to, there's a 50-50 probability of it going to 0 or 1. It's great. So we did up, down. Now we did towards you, right? To the left. Now, this is what happens when we apply a Hadamard gate to the 0 state, okay? Now, if we wanted to apply to the 1 state, how would we do that? Great. So if we uncomment this, right? Which means that we're applying a NOT gate, and then we apply a Hadamard gate, okay? So now our qubit's at the 1 state, which flips it down. Then we apply a Hadamard gate, okay? And we went over the math in this last time, okay? And if you guys want to see that part of the whiteboard, okay? But as you can see, the state for Hadamard onto 0 is not the same as Hadamard onto 1. Do you have a question? Oh, okay. So as you can see, now this is pointing back, right? So it was pointing this way for just Hadamard onto 0, and it's pointing that way okay, or Hadamard onto 1. So one thing, I'll get to your question. One thing that I do not want there to be a misconception of is, oh, the Hadamard gate is just rotating around this axis, right? It's just, as you can see, we did not just do this from 0 to here, and then from 1, sure. For these purposes, it kind of rotated like towards us, but that is not what this gate actually does, okay? It might look like that for these two inputs, but for other inputs, that's not what it does, okay, right? If we, actually, let's demonstrate that. Let's go back to our, yeah, we can initialize 2 qubits.
We're just working.
Yeah. If we go back to our single Hadamard, okay, we see that it's in this state. So what happens if we apply Hadamard again? We went over that last time in class, okay? And if you guys want, you guys can go through the math over and over again. Yeah, so it goes back to 0, okay? And if you guys want me to show you why that happens, I can do that. But during class from now on, we're just gonna start short forming things. 2 Hadamards is the same thing as an identity gate, okay? So yes, he's absolutely right. If we apply another Hadamard gate, we get back to 0 state. And so this kind of proves that it doesn't just rotate around that y-axis like this, right? Because for x, or when it was in the plus state, it went back up. Okay. There are some gates that, or there are some gates that you can call that will just do the rotation around the y-axis or x-axis or whatever axis you want. Okay. But that's not this. Okay. Now, so we saw a single Hadamard, right? And then the same thing happens if we did a Hadamard to a 1 state. And then if we apply another Hadamard, okay, so it's we are at the 1 state, then a Hadamard, then another Hadamard. As I said, 2 Hadamards, they cancel each other out. So it's essentially like applying an identity gate. So we did X, then identity, which is just an X, which is why you get the 1 state. Okay, does that make sense to everyone? Okay, so do you see how this can help us like visualize where we are in the block sphere? And okay, obviously if you're in the 1 state, right? And if you measure it right now, you'll measure out to a 1, right? Same thing with 0. Okay. If we look at the what is it? The plus and minus state in math terms, right? It was, I'm just gonna type out for the people who are on Zoom. So if you look at these 2 equations right here, it's 1 over root 2, 0, plus 1 over root 2 of 1, right? We have that, right? So the X gate, we know, transferred from 0 to the 1 state. But do you guys think there would be a gate that could go from a 0 or a plus to the minus state? Seems like there should be, right? Let me quickly type this out. Yeah, this is not an actual coding thing, so. Ooh. Things that Hadamard, not Hadamard. Okay. Let's try that. Okay. Oh, this one I was just writing out. You guys can comment this out. Okay. So he said Hadamard, not Hadamard. So let's think this through first. Okay. To go from plus to minus. Oh, you want from plus to minus, you want to do a Hadamard, then a not, then a Hadamard. Okay. So let's do it like this. We're gonna first initialize, right? That's what this is gonna. We first want to initialize into the plus state, and we do that by doing qc.h. Okay, and then we're gonna do our transition. Okay, so he thinks we start off in a Hadamard, right? So, sorry, we start from the 0 state. Then we apply a Hadamard, and now it's in the plus state. Okay, so you're saying to go back into Hadamard, then we not, so that flips it to a 1. Okay, and then you say do a Hadamard, so it's a minus. Does anyone think that'll work? Okay. So this is our circuit. Okay. And we get the minus state. Nice job. Okay. Now, there's 2 ways to look at this. Okay. If we look at our circuit, this is why it's good to print out the circuit. We have a Hadamard, right? If we ignore initialization, we broke down the comments. Oh, by the way, if you guys want to visualize like certain sections of your circuit in code, you can do qc.barrier. And what that does is just create a little wall. Okay. So we have a Hadamard and Hadamard. Those 2 would cancel out, right? And then we have an X, then an H left, which is just you apply not gate, an H, which will get us to the minus state. So that's one way to look at it. Okay. Yes, right. So this would simplify, the first 2 gates would simplify to an identity matrix, which is, we can ignore that. Then not in Hadamard, like you said. Okay. So there is a matrix that will also do this HXH, okay, which is called the Z matrix. Okay. So yeah, that initialization was just to get us to the plus state, but we kind of use it in our circuit to cancel out. Okay. Oh, and I know we're running out of time, so this would be like the last thing we do. Okay. So if we comment out the transition. Oh, okay. So you can do control/ if you want to group comment stuff. If you just do qc.z. Okay. Now if we print, we get the same thing. Hadamard and then that Z. Okay, now let's think about this. From 0 to 1, we did the X gate. That rotates 180 degrees. Now this gate actually does a true rotation. It rotates 180 degrees about the X axis, right? That's why I went from 0 to 1. A Z gate, right? It'll rotate around the Z axis. So this is the Z axis. And if the arrow's pointing this way, and we do a Z, it'll rotate 180 degrees and it'll point back. Does that make sense? Good. So what happens if we do another Z? It'll cancel out. So that's another identity, right? 2 Z's are going to make an identity. Okay. Well, yeah, the Z gate is a unitary, and
The math behind it, yes, but as a visualization.
Yeah.
Show why.
if you guys want to, I think you guys might have written this out last time, but here you go. The Z matrix is going to be just like the identity, right? Except we have a -1, okay? And why this -1? We will go into that next time, I guess. Okay, but yeah, so we will look into the math behind this, but now you guys have some sort of like mental image of like what happens when you apply a Hadamard to a qubit. You can think, oh, okay, it kind of like rotates to me. Obviously, don't say that to your like quantum mechanics professor. He's gonna be like, what are you talking about? But yeah, in my mind, I'm like, okay, so it rotates, and this will be much more helpful when we go into like breaking things down, like what rotations along around the Z-axis can you do, right? When you combine rotations, that's when it starts getting a little bit tricky. And if you want, it's easy to print this out. You can print out your circuit using this command. So I recommend you guys save it or comment it. If you guys want a list of like important commands, this is a really useful one. Okay. So, yeah.
So this concludes learning labs for today. Next time, we're probably gonna go over multi-qubit states and some of the important gates within that. So like CNOT and control gates, etc.
Yes.
Okay. So thank you all for tuning in. Thank you guys for coming, and we will see you next time.
So I'm gonna be staying here for a little bit. For other reasons, but if you guys have any questions, yeah. Like, is that what makes it?
No, just like, at least my interpretation.
Wait, no. Did it stop recording? No. Did it stop recording midway? Oh, no.
Thank you.
Yeah, thank you for coming.
Oh, are you there?
No.
Just, oh, right.
That's crazy. It stopped recording midway.
How does that relate?
Okay, okay. So this is a very good question.
Okay. Probably send you a comprehensive.
So, remember, were you there first?
Yes, maybe it would be.
Okay, that's fine. So, and
Screw technology. I hate technology so much.
okay, so, that interpretation, you see how it seems like it's like a block here, but divided by two? Like,
Yeah, it's like
it's 90 degrees.
and then it's just 2D.
Yeah, so we can ignore the 2D part for now. But do you see how the 1 side is here, 0 side is here, and then some is back. If you multiply all the angles by 2, you would get 1 and 0, right? Parallel to each other. Yeah. Plus and minus would be parallel. Yeah. So this is in quantum optics, which is basically you're gonna use lasers